Welcome. We now start learning about machine learning models in the context of trees, specifically the so-called decision trees. So these objects or mathematical artifacts from graph theory find application in machine learning in the sense that you can use a decision tree for classification tasks or for regression tasks. And perhaps the best way to understand this is actually building a tree based on a data set. But in a nutshell, what we would like to do is to exploit the information provided by columns or features to then ask multiple questions that can integrate the structure of a tree. So let's refer to a familiar data frame that stores information about adoption of pets in a no-kill shelter. So what we're seeing on the screen on the right-hand side is a subset of this data frame. The column that's called X1 contains information about the actual age, the chronological age of the animal, of the pet, in units of years. So there is X1. X2 is the second column, which contains information about it's another type of clock. It's the time until basically the residence time in the shelter in units of months. And then the label or the target here is whether the pet is adopted. So a 1 would be a yes. So whether we have values of 1. So we have values of 1 in a few instances there, which means successful adoption there, and 0 if the pet was not adopted. So now we're going to define what we have on the left-hand side is a tree where the nodes or vertices involve information that's obtained from specific features. For example, we are going to have conditions based on the measurement or value that's stored in one feature. What the condition you see here at the top is about, let me use the highlighter, is about whether or not the feature X2, which has to do with that residence time until adoption, is basically max at the value of 5. So is less than or equal to 5. That's a condition on that feature or second column. And then if, so this is a yes or no, success or failure, whether this condition is satisfied. If it is, it goes on one branch. If it is not, then it goes on to the other branch. So that's where we're seeing here the yes or no relative to either edge or link out of that specific node. So the scenarios we have there is that if that value of amount of time until outcome is less than or equal to 5, if that is true, then the branch goes on the next node, which has a condition on the first feature, on the first column. But if that is not satisfied, then it goes on to a link or an edge pointing to have the value of class equal to 1. So remember here, the value of equal to 1 is basically what we have recorded on the third column, which is the target or label. So the third column here is called class in the sense of classification, or it can also be called category, in the sense that this third column is storing measurements for a statistical variable that is categorical, right? So we call the groups or categories, or we may also call those classes. Classes as in classification. And so that's what you see some notes here as saying class equals 1, because here the class or the category may take one or two values, either 0 or 1. 1 for yes adoption, 0 for no, it was not adopted. So the way we read the tree is we started with this condition. If that condition is satisfied, it goes into another condition, another node that has another condition relative to x1 to the first column. That has to do with being being less than or equal to 4.5. If that is a yes, then it leads into having a value of 0 for the adoption outcome. If it is a no, then it is another condition based on the value of the store on the second feature to the second column. And that is another constraint about being exceeding 3, being equal to 3 or greater than 3. If that is satisfied, if that is a yes, then the categorical value takes the value of 0. Or if it is a no, then the categorical value takes the value, the categorical variable takes the value of 1. So there is definitely a sense of direction as one would navigate or traverse or travel, right? So here the idea with trees is that you're always going from top to bottom, right? And so here the initial node starts with this condition, and that node is called root node. And then we may start navigating, going going down from that node. And so just as a reminder, that node is called root node and is basically the point of departure or the starting point here with a condition. So we refer to where we start, the so-called root node. Some of the other nodes are going to be considered split nodes. Those are nodes in which one would split the data points into some branches. And in the literature, split nodes are also called decision nodes, internal nodes, or sometimes parent nodes. So for example, we may start with this condition and then go along this branch and then move on to this branch. And so this is just kind of reinforcing the type of examples, nodes for this scenario, which would be considered split nodes. So the root, which is the beginning going from top to bottom, it's the root node is also considered a split node. So we continue kind of reviewing terminology. The other technical term here that is used is leaf nodes. Those are considered destinations or final locations in the tree. When we reach a leaf node, then there is no need to do any more splitting of the data points. Instead, at that final location, one would make predictions. So each leaf node would have a dedicated value to return. And for example, in what we see illustrated here, the leaf nodes have been coded with the possible values according to the categorical statistical variable, or according to this. In this scenario, it's like certainly a classification, but it's a binary situation of having only two values, 0 for no adoption and 1 for successful adoption of a pet.